Thermal management is something that's come up several times today as we look forward to how to achieve ultra-low NOx standards and balance those with greenhouse gas standards. So we're very glad to welcome Jeff Diestelmeier to the stage. He's Chief Systems Engineer at Watlow. Welcome back. Jeff is with Watlow, where his role is, as I said, Chief System Designer. In this role, he's responsible for global business strategy and product development for Watlow's diesel emissions business. His primary area of focus is, I'll tell you in a minute, developing thermal technologies, innovative and breakthrough thermal technologies for improved engine and after-treatment systems performance. And he's got a career involved in engine design, even in the aviation business, so some interesting background. We know that this issue of heat and thermal management is so important, so we look forward to hearing from you, Jeff, looking at how you can use thermal energy to improve the NOx control in SCR and allow us to get closer to where we need to be in terms of that ultra-low NOx control. So the stage is yours. Over to you.
All right, thank you very much, Tim, and good afternoon. The presentation that I'm going to share today is based in large part on an SAE paper that we presented at the World Congress in Detroit this past April. So I'd like to acknowledge the co-authors, Dave Culbertson, James Pradon, both of Watlow, and Dr. Magdi Kher of Mag Diesel Technologies. Here's an outline for the presentation. I'll just give a brief introduction of Watlow and what we do, the motivation for our work here, the need for thermal energy, which has been talked about quite a bit already today, methods of providing that thermal energy, of heating the exhaust gas, some work that we did with an initial design of an electric heater, and then more recent work that we've done on a 24-volt version, and then finally some conclusions. Our core purpose at Watlow is enriching the lives of others through inspired innovation. And we tend to be the company that gets called for some of the toughest thermal problems that need to be solved. And we help others in these various industries such as semiconductor, energy process, and of course diesel emissions, also medical and clinical analytical type applications. We are a privately held company based in St. Louis, Missouri, and we're third generation now. Peter Deloge is our CEO. He's the grandson of our founder. This year will be north of $400 million in terms of annual revenue. We have a presence all over the world with sales offices, 11 manufacturing facilities, and 3 advanced technology centers, including one in Europe. And we have over 2,000 team members worldwide. In terms of our involvement in the diesel business, we've been in that industry for over 40 years, and we make products that include heaters and temperature sensors for a variety of both on-engine and after-treatment applications. And we are involved in pretty much the traditional market segments. The only one that we don't participate in is the passenger car segment. So the motivation for the work that we've been doing with heating the exhaust gas really is driven by this fundamental goal that we have in the industry of improving the diesel engine efficiency, in other words, getting more fuel efficient, while meeting more and more stringent emissions regulations. And today, of course, we have a strong focus on CO2 reduction and increased fuel economy. And we're talking about tightening the NOx requirements, whether it's CARB and the ultra-low NOx, or things like problems with real driving emissions in Europe, where we know we have higher NOx emissions than what we desire. So how can we achieve really the 2 fundamental needs, improving efficiency while meeting tighter and tighter emissions limits? I think it's helpful on this topic to just kind of come back and spend a few minutes on some of the fundamentals of a heat engine. And when we have a heat engine, we basically provide it with fuel. So it's chemical energy in the form of fuel, and we provide it with air. And then upon combustion, we expect the engine to perform work. And along with that work then, we also have some losses. So we have thermal losses through the cooling system, and we also have thermal losses through the exhaust system. And when we think about today's diesel engines, we're really, in terms of the efficiency of converting that fuel energy to work, we're really in the neighborhood of 45 to 50%, even beyond 50%. So much higher than we were, even 5 or 10 years ago. And that's really positive from the standpoint of fuel efficiency. But when that part of the equation goes up, the other part goes down. And so we have less thermal energy then that's being discarded or lost through the coolant system and through the exhaust. And that doesn't bode well from an emissions standpoint. When we look at SCR technology, the technology's been used here in heavy duty in the U.S. for a good 8 years now, and in Europe prior to that. So we can say we've got at least a decade of good experience with catalytic NOx reduction. And we know that SCR technology works very well when we have the proper temperatures. Of course, there's a drop-off in terms of efficiency if we get too warm. But mainly, we focus ourselves on the left-hand side of that graph and the conditions where we are lower in temperature than what we need to be to get the kind of NOx conversion that we desire. So really, in order to meet the new ultra-low NOx target that CARB has put out there, we need to be achieving greater than 95% conversion efficiency on an FTP 75 cold start test in order to achieve that 0.02 grams per brake horsepower hour. And looking at the three major catalyst formulations that are used in the industry, it's pretty easy to see that temperatures ranging from 200 to 350 degrees C would be the most beneficial during cold start and warm-up for that to happen. When we consider then different means of heating the exhaust gas to heat those catalysts up, there's really two major pathways. The industry has engine-based methods, and we also have exhaust-based methods. So here in these two simple illustrations, the engine-based methods, we're really trying to drive thermal energy from the engine itself through the turbocharger and the exhaust system, and ultimately to the catalyst where we need the heat. In the case of exhaust-based heating, we place a heat source much closer downstream, much closer to the catalyst, and we provide the thermal energy at that point. Now, amongst the various engine-based means that we have available to us to increase the exhaust gas temperature, we have things like intake air preheating, or intake air throttling is another common one that's used. Exhaust air throttling is a common one. Some companies use EGR as a means of heating the exhaust, cylinder bank cutouts, or late post injection of some fuel. And regardless of which method is chosen, we can say that all of these measures consume more fuel than if we were not employing them. A little bit further, with respect to engine-based means, there's really no silver bullet measure. In other words, if we pick any one of those on that previous slide, there's no magical formula that's going to achieve the result we want and minimize the consumption of fuel. Certainly, it's true that some companies use combinations of various methods in tandem, and that can be more effective. Each engine-based measure does bring its own set of challenges to deploy it. Some definitely adversely affect the durability of the engine, and most, if not all of them, fail to reach the kind of temperatures that we need for catalyst desulfation. And also, most of, if not all of those measures are unable to prevent urea deposit formation. In terms of exhaust-based heating methods, there are really three primary methods that are known to the industry. We have burner systems or open flame. We have hydrocarbon dosing. Some might refer to that as a catalytic burner. And then we also have electric heat. Again, it's true that all three of these measures consume fuel as well. So there is no such thing as free thermal energy. And whether we're providing it from the engine or we're providing it in the exhaust itself, it's going to cost us some fuel. But which measure we choose really depends on the cost and the effectiveness of that measure, and then also taking into account things like durability and serviceability. This is an example of a burner system. So probably the company that's most known for burner systems is Caterpillar. And Caterpillar implemented the burner system back in 2007 when they were still in the on-highway heavy-duty engine business. And the burner is probably the most energy-efficient way of converting fuel energy to thermal energy for use in the after-treatment system. But the burner system comes with a lot of issues. Certainly, one of the biggest challenges is keeping the flame lit as the DPF fills up with soot, and we realize greater and greater back pressure. It's more and more difficult to keep the flame lit, and so supplemental air supply has to be provided. There's also issues with the cost of these systems, and then a burner system is largely unattractive to certain parts of the market. Hydrocarbon dosing is another method. And so in this method, we basically dose fuel either post-injection from in-cylinder means or with a seventh injector in the exhaust pipe. And the idea here is that we get a chemical reaction when that fuel comes in contact with the precious metal inside the diesel oxidation catalyst. We get an exotherm, and that's where the thermal energy comes from in this case. And then finally, the third alternative, and the one we'll spend the rest of the time talking about today, is the use of an electric heater. And so this does provide heat directly in the exhaust, as do the other methods. And we do that with a resistance wire and applying power through that resistance wire. And the relationship of the temperature increase is shown in the equation there on the right-hand side. So basically, we have to determine what kind of change in temperature are we looking for. So the difference between the temperature on the outlet side of the heater compared to the temperature of the exhaust gas coming into the heater, that delta T then multiplied by the mass flow rate and the coefficient of energy in the exhaust. And so we end up then taking that into account, but we also have to take into account thermal efficiency losses from the heater itself. And generally speaking, the heater will lose about 10% thermal energy immediately to the environment adjacent to it, and so we have to take that into account as well when we determine the kilowatt rating of the heater. So we took and did some initial work with an electric heater in a diesel hybrid electric test setup, and this was done on a Cummins ISDE 6.7 liter engine, and this was set up in a configuration that would be used in a diesel hybrid electric application. So for example, a bus that operates as a hybrid bus, this would be the configuration of such a system. And the original prototype that we worked with was rated at full power of 30 kW. It had 6 elements inside of it, and each of those elements was capable of being turned on and off. So we had up to 30 kW available. We placed the heater upstream of the DOC, downstream of the turbocharger, and we had temperature sensors at various points in the system. SCR inlet, SCR midbed, and tailpipe were the ones that we were mostly concerned with. The heater itself was about 10 liters in volume. As I said, there was 6 elements inside of the heater. Each one of those 6 elements was rated at 6 kW, and we were powering on anywhere from 5 elements inside the heater, and anywhere from 2 to 5 elements at a time. So we could go from 12, 18, 24, and 30 kW. And then we had an internal temperature sensor inside the heater. And the purpose of that temperature sensor is to make sure that we don't overheat the elements and cause the heater to fail. A little bit more detail regarding the design of electric heating elements. This is a very typical kind of configuration that we used in this prototype heater and is often used in the industry. And the heater element consists of a resistance wire, so that's the part that gets hot when we apply electricity to it. We have, surrounding that, we have magnesium oxide, and then we have an outer sheath, and those are the basic elements of the heater. Now, the mineral insulation, or magnesium oxide, serves 3 functions. It's first there to electrically isolate the resistance coil from the outer sheath, so we don't conduct electricity to the outer sheath. It's there to protect the coil from vibration, so it's very tightly compacted around that wire. And the reason that we worry about that is when we think about putting a heater on a vehicle, whether it's an on-road or off-road vehicle, we know we have a variety of vibration profiles that come into play. So we have to make sure the heater's going to be robust from that standpoint. And then the final purpose of the MGO is to conduct thermal energy away from the resistance coil to the outer sheath. Then the heat can radiate from there to the exhaust. The heater is controlled to achieve a certain target temperature, as we talked about in the equation. And we also must limit the power to the heater so that we don't burn up the resistance coil and fail the heater. In this particular test, we took and powered the heater all the way to 30 kW, and our goal here was just to see how far we could heat the exhaust for the first 400 seconds. So we started from cold, and we powered the heater on, a full 30 kW. And the part I'd like to call your attention to is this line right here, sort of a brick red color. And that line represents the heater power. And so you can see almost immediately at the beginning of the test, the heater powered up and was at 30 kW. If you read that off to the right side, 30 kW for heater power. But you can also see that about 150 seconds into the test, the heater started shutting itself on and off. And the reason for that was the internal temperature of the heater reached a danger point. And so the logic of the smart power switch was to turn that heater off and keep it below the danger zone. We did that same test, but configured the heater for only 12 kW. Again, the purpose was to just see how far and how fast we could heat the exhaust using 12 kW. And here, in this particular case, here again is that heater power. And you can see where, in this case, the heater was basically on the entire time. So what was happening was we were conducting enough thermal energy away from the heater element to the exhaust gas that we kept the internal temperature of the heater below the danger zone. After doing that test at various kW levels, what we see is that for the case of the 24 and the 30 kW heater, those heaters were not on for the entire length of the test. We were operating with the on-off in order to protect the heater. And so even with a heater volume of 10 liters, we were limiting the power output in order to protect the heater. So we took that work and continued onward. And we ended up developing this product here, which we call our Gen 1 product. And we released this to the market. And we mainly intended this for highly electrified applications, such as diesel gensets. You can see on a break, if you want to stop by our booth, you can see this product on display. It looks like this, and it's designed to operate at 350 volts DC, meaning that you'd have to have generator power right there in order to power the heater. So we said, well, this is fine for those kinds of applications, but if you want to put this kind of a heater onto a moving vehicle, we're dealing with a much different scenario than 350 volts DC in most cases. So we had some improvement in objectives in mind, and we wanted to reduce the size and the cost of the heater. We wanted to reduce the back pressure that it creates in the exhaust. We wanted that rapid heating capability without the danger of overheating the elements, and we wanted it to be feasible for the power budget that you'd have on an on-road vehicle. And so our design work took us in this direction, and this is a 24-volt heater that we developed, a prototype. It's very small and compact, much smaller than the other unit above it. It's about 5.5 inches in diameter, and it's about 3 inches in width, and it operates at 24-volt DC. One of the features of this design is that is a wrapped corrugated structure around the heating elements, and the purpose for that actually is several purposes. The first one is that corrugated structure provides some desirable natural frequency of the heater with some damping, so we've got much better vibration resistance. It also enables better thermal conductivity from the heater sheath to the exhaust gas. So effectively we're increasing the surface area right adjacent to the sheath, so we have more metal surfaces to conduct the thermal energy, transfer it to the exhaust gas. And then lastly, that corrugated structure does provide some mixing as well. To go along with that heater, we developed this new 24-volt smart power switch, and it's capable of switching 300 amps in 250 amp circuits. It's rated to 105 degrees C in terms of the internal hardware. It makes real-time power measurements so that we're able to capture both heater voltage and current. It has a heat sink underneath it for mounting to the frame of the vehicle, and it is J1939 CAN bus enabled. So it's able to read information on the CAN bus coming from the ECU. It's also in turn able to communicate information back to the ECU. So the smart power switch then protects the resistance wire while enabling rapid heating during the transient and cold start operation. So we took that prototype heater and we fashioned a can around it and some inlet cones, and we just did some basic testing. So we powered that heater at 29 volts DC, and we operated at 4.1 kW. And as you can see there, back on a 6.7 liter Cummins engine, we were able to increase the exhaust gas temperature by close to 30 degrees C in about 200 seconds of time. When we compare that design versus the old design, you can see there's a significant difference in the temperature output of the heater. So whether it's at 10% load or at 30% load, you compare the solid lines and the dashed lines, and basically the new heater plus the smart power switch enabled us to achieve about 1.7 times higher temperature increase, while at the same time reducing the size of the heater by well over 50%. So much smaller and more compact package, and certainly less back pressure. As been reported, CARB has been doing some work together with Mika at Southwest Research Institute, and just wanted to remind everyone of kind of one of the key takeaways of some of that work. This is on a 2014 Volvo 13-liter engine, and after all of the screening tests that were conducted, this was the preferred configuration to try to meet the ultra-low NOx level. And one of the things that was critical to that was this mini burner, and the mini burner provided about 10 kW of supplemental energy to the exhaust. So one way or another, to meet the ultra-low NOx limit, we're going to need to add some supplemental thermal energy to the exhaust. So kind of in that spirit, we came back to our 24-volt heater, and we said, well, what can we do with this 4 kW heater on this 6.7-liter engine? So here's the test setup for that. We put the small heater out in front of the DOC. We measured temperature at various points in that system. And then we powered that heater actually from the alternator on the engine. So we had a 150 amp, 150 amp alternator. We had batteries, and we operated as 24 volts. And that was the test configuration that we used. So just one example of the results that we obtained with this heater. This is a city bus cycle, and on that 6.7-liter engine, ISB engine, and you can see what the SCR temperature was without the heater. So it was pretty much a steady 150 degrees C throughout that cycle. And at 150 degrees C, we're not going to get really good NOx conversion, probably in the order of 50%. And we're really below the level that you'd want to try to even dose urea. So, not very good in terms of the implications for the NOx. But when we powered that little heater up, we were able to increase the exhaust gas temperature to 200 degrees C. So now we're in the range, well within the range where we can dose urea, and we're certainly confident that we're going to get decent NOx reduction depending on the catalyst that we're using. So approximately 4 kW of thermal energy enables much higher NOx conversion efficiency, and that 4 kW comes straight from a standard 24-volt DC system available today. So we're not talking about 350 volts, we're talking about a 24-volt system. One can then start thinking about the potential for this, and you could package that little heater inside of the after-treatment system can, and you could compare that with the alternative that's often used today, intake air throttles and EGR, and one can envision that you could get rid of the EGR, allow for higher engine out NOx, and deal with cleaning that NOx up by having the heater right there in the after-treatment system. So in conclusion, tightening regulations are clearly demanding a reduction in CO2 and NOx, and certainly improvements in fuel consumption, and making it an ever-increasing need for more thermal energy in the after-treatment system. An electric heater can provide many benefits over traditional engine-based heating, and development efforts at Watlow have resulted in a much smaller, lower cost, and certainly more feasible heating system for an on-road vehicle. Just like to acknowledge many folks at Watlow that contributed to the work, and thank them for their contributions. There's the references, and I thank you very much for your time.
Thank you, Jeff. Once again, we have time for a question or two before we move on. Jeff, maybe I can start with a question, as is my way. You mentioned the three ways of heating the exhaust early on in your presentation: the burner and the catalytic hydrocarbon approach, and then your heater. With the focus on greenhouse gas emissions and fuel consumption, have you ever done any comparative tests to see which is more fuel efficient for the same level of thermal energy addition to the exhaust? Let's say 4 kilowatts or 12 kilowatt addition?
Yeah, clearly, as I mentioned in the presentation, clearly a burner will be the best, most efficient conversion of fuel energy directly to heat. However, there are many issues associated with a burner, and it's difficult to deploy in a practical manner, and also it's not desirable in many applications.
Yeah. So your system would be simpler to implement and far fewer components.
Correct. Yep.
Yeah. Any questions? Yes. Let's have Sorry, go ahead, sir.
Yeah, Colin Nice from Cummins. Jeff, two questions. One, AC versus DC. At what point does DC stop making sense in terms of power output? And then the second question is, what are the trade-offs between exhaust heating, like you showing with the Watlow heater, and direct element heating, as in heating the catalyst element rather than the exhaust gas?
So the first question was AC versus DC. We see 24 volts DC as being very practical, and with the 48 volt systems that are now clearly coming to the industry, a 48 volt system would be very practical DC in an application such as a 13 liter or 15 liter on-highway truck engine. So comparable amount of thermal energy could be created on a 48 volt system with a 10 or 12 kW heater, and DC would be the way to go for that. Your second question, Colin, was?
So it's about whether heating the exhaust gas versus heating the catalyst element, what are the trade-offs that you see between those two approaches?
We've talked about that as a company, and we've been interested in heating the catalyst itself directly, but you run into issues where how are you going to embed the electrical elements in the substrate where the catalyst is deposited, and then as those heating elements warm up and expand and contract, what are you doing to the deposition, the catalyst that's been deposited on the substrate? And we think those are pretty significant challenges. So even though we'd like to directly heat the catalyst, there are a number of engineering challenges associated with that, and so that's why we've leaned in the direction of putting the heater out in front.
Thank you. We have a question at the front from Bill.
This is following up on Tim's comments about the looking at what kind of emissions benefit we get versus the greenhouse gas implications. And this is a very beautiful, elegant sort of way to just heat the exhaust in a simple way. It has kind of a continuous use aspect to it in certain applications. Have you looked at places where using just a little bit of heat may allow dosing or conversion of the DEF in a way that would allow sort of bootstrapping systems or dosing at levels where they're getting partial conversion efficiency and those kind of things, and the sort of on the using these kind of concepts on the DEF side and maybe not in the full flow exhaust?
Yes, we certainly have looked at those concepts. Actually, the testing that we've done thus far suggests that the use of the heater is really the best place for that is on cold start or some of these challenging real-world duty cycles. So once the engine and the after-treatment system warm up, if we're maintaining enough load on the engine, we don't need to add the extra heat from the electric heater or any of the other methods for that matter. So what we find is that cold starts or low load duty cycles actually are really the right strategy to think about using the heater. Whether it's to get the SCR catalyst up to temperature, whether it's the advantage of putting the heater in front of the DOC is to start making some NO2 pretty quickly, get the DOC up to temperature, start making some NO2, get the ratio of NO to NO2 much more favorable for, let's say, a copper zeolite catalyst, and enable that urea dosing at whatever temperature the OEM is wanting to do that, but much sooner in the cycle.
Makes a lot of sense. Jeff, I'm afraid we need to move on, but thank you very much for sharing that with us and for the questions. Thank you.